Hello viewers. In this session, we'll be taking up two sample t-test and pair t-test. So let's start with what do we understand by two sample t-test? The two sample t-test, which is also known as independent sample t-test, is a method used to test whether the unknown population means of two groups are equal or not. So, a question may arise in your mind, is this the same as we have done A/B test? Yes. A two sample test is used to analyze the results from the A/B test. Now, you may ask, when can I use this test? So, of course, you can use this test when your data values are independent, are randomly sampled from two normal populations, and the two independent groups have equal variances. So, you need to keep in mind these 3 points that your data values are independent, randomly sampled, and are independent and have equal variance. So, what will you do if you have more than two groups? Of course, in that case, you can use multiple comparison method. You can use like ANOVA is one of them. You can use multiple comparison methods like Tukey-Kramer test, which will do pairwise differences. You can also go for analysis of means, that is ANOM, to compare the group means to so that you can have overall mean. You can also use Dennett test to compare each group mean to a control mean. Now you may again ask one question. What if the variances of my two groups are not equal? Of course, you can still use the two sample t-test. You use a different estimate of the standard deviation in this case. What if your data is near not normally distributed? So what will you do in such cases? See, if your sample sizes are small, you might not be able to test for normality. You might need to rely on your understanding of the data. When you cannot safely assume normality, you can perform a non-parametric test that doesn't assume normality. So before I proceed further, let me just tell you something about the normality, testing of the normality. So as we can see, the normality assumption is more important for small sizes sample rather than for larger sizes sample. So normal distributions are symmetric, which means they are even on both sides of the center. Normal distributions do not have extreme values or are outliers. We can check these two features of a normal distribution with graphs. Okay, like in the previous case, if you remember, we have decided about the energy bar data, which was close enough to normal to go ahead with the assumption of normality. Okay, so here we can see the figure and we can say that a normal quantile plot for the data, and this is like supporting our decision. So we can see that we can also perform a formal test for normality using software. Okay, and one of the figures which we can see on the slide is the result of the testing for normality. And here we cannot reject the hypothesis of a normal distribution. And we can go ahead with the assumption that the energy bar data is normally distributed. Here, when we are doing it with the software, goodness of fit test also comes in this thing. So we can see from the goodness of fit test also whether it is a normally distributed or okay. So now coming to the two sample t-test. Okay, so in this section, basically we are focusing and we will first check when to perform this two sample t-test, and then we will check our data also, and then we will also learn how to perform the test and the statistical details involved in this test. So now before proceeding, what are the things which we need to know? For the two sample t-test, we need to have two variables. That is the first prerequisite. One variable defines the two groups, and the second variable is the measurement of the interest. So, like we should also have an idea or hypothesis. That is what which we want to accept or reject. That is the means of the underlying populations of the two groups are different. Okay, so let's understand it through a couple of examples. Like, for example, we have students who speak English as their first language and students who do not. All students take a reading test. Two groups are the native English speakers and non-native speakers. Now, our measurements are the test scores. So, our idea is that mean test scores for the underlying population of native and non-native English speakers are not the same. We want to know if the mean score for the population of native English speakers is different from the people who learn English as a second language. So we measure, like in the previous example, if you remember, the grams of proteins in two different brands of energy bars. Our two groups were the two different brands, and our measurement is the grams of proteins for each energy bar. So our idea or hypothesis was that the mean gram of the protein for the underlying population of the two brands may be different. Now we want to know if we have evidence, enough evidence that the mean gram of the proteins for the two brands of different bars is different or not. So we can conduct a validate or we can validate a test. So what will be the assumptions underlying it? Data values must be independent. That means measurements for one observation do not affect the measurement of any other observation. So data in each group must be obtained via random sample from the population. That is, data in each groups are normally distributed. Data values are continuous. The variances for the two independent groups should be equal. And for a very small group of data, it can be hard to test these requirements. So, what to do then? We have to check whether our requirements are being met or not. Okay. So let's do one two sample t-test with an example. Like one way to measure a person's fitness is to measure their body fat percentage. This is one example which I'm taking with you people. Now, average body fat percentage vary by age, but according to some guidelines, the normal range for men is 15 to 20% body fat, and the normal range for women is 20 to 25 body fat percentage of body fat. Now, our sample data is from a group of men and women who did workouts at a gym 3 times a week for a year. Then their trainer measured the body fat, and the data was collected, and it has been displayed in the form of a table. So, like men, we can see the groups are men and women, and here we have body fat percentages. So this table clearly we can see some overlap in the body fat measurements for the men and the women. But we can also find some differences. So just by looking at the data, it's hard to draw any solid conclusions about whether the underlying population of men and women at the gym have the same mean body fat. Now, that is the value of a statistical test. So, the statistical test over here can provide a common, you can say, a valid way to make decision so that everyone can come out with the right idea. Now, let's start by answering the question. Is the two sample t-test an appropriate method to evaluate the difference in body fat between men and women? The example which we have taken in the previous discussion. The data values are independent. So the body fat for any one person does not depend on the body fat of the another person. So we assume the people measured represent a simple random sample from the population of members of the gym. We also assume that the data are normally distributed, and we can check this assumption. So the data values are body fat measurements. The measurements are continuous. We can also assume that the variances for men and women are equal, and we can check this assumption. But before jumping into analysis, we should always take a quick look at the data. So here we can see the figure, the histogram, and the summary statistics for the men and women. And we can see over here that the mean is 14.95 for men, standard deviation is 6.84, standard error of mean is 1.90, and we can see the upper and 5% risk, it is 19.08, and the lower at 5% risk is 10 point, and the total number of sample we have taken is 13. Same way we can see, even if we plot on the histogram, you can see over here it will be like a normal distribution only, bell shaped only. Same way we can see for women, mean values is 22.29, standard deviation is 5 point. So likewise we can see the statistics. This is a summary statistics, and even for women also it is almost going like a bell-shaped curve. So the two histograms, they are on the same scale. So we can see that there are no very unusual points or outliers. So data also looked roughly bell-shaped only. So our initial idea of normal distribution seems reasonable. Now, if we want to explain the summary statistics, we can see that the standard deviations are similar. And this supports the idea of equal variances. So we can also check this using a test for variances. So now based on our observations, the two sample t-test appears to be an appropriate method to test for a difference in means. Now question arises how to perform this two sample t-test. So here I will guide you how to perform it. For each group, we need the average, we need the standard deviation, and we need the sample size. So in the example which we have taken for the men and women, we can see the sample size is 10 for women and 13 for men. Then average is 22.29 for women and 14.95 for men. And standard deviation is 5.32 for women and 6.84. So without doing any testing, we can see that the averages for men and women in our samples are not the same. But how different are they? Are the averages close enough for us to conclude that mean body fat is the same for larger population of men and women at the gym? Or are the averages too different for us to make this conclusion? Now, this I will explain you further by the principles underlying the two sample t-test in the statistical details. But let's first proceed through the steps from beginning to the end. So we start by calculating our statistic, and the calculation begins with finding the difference between the two averages, that is 22.29 and 14.95, and we take the difference of it, it comes to 7.34. So here we have seen that the difference is 7.34. Now the differences in our sample estimates the differences between the population mean for the two groups. So next we will calculate the pooled standard deviation. Now this builds the combined estimate of the overall standard deviation. The estimate adjusts for group sizes. So first we calculate the pooled variances. So here we have the pooled variances, that the formula is n1 minus 1 into, we can say, s1 square plus n2 minus 1 into s2 of the whole square. And similarly, we put the values. So n for the first group is 10, for the second group it is 13. So we are putting 10 minus 1, and the 5.32 is the standard deviation. So 6.84 is the standard deviation for we can say the group which has n13, and n1 plus n2 minus 2, so that is 10 plus 13 minus 2. Here you can see this we are here, and then calculating the values we will get answer to be 38.33. This is what is the, you can say, pooled variance. So now we take the square root of the pooled variance and we get the standard deviation. That is, here you can see under root 38.88, and this comes to 6.24. We now have all the pieces of our test statistics, and we have the differences of the averages, the pooled standard deviation, and the sample sizes. So we calculate our test statistics as follows. So T is equal to difference of the group averages is divided by the standard error of the difference. So difference of the group averages is 7.34 and the standard error of the difference is 2.62 doing this calculation. So here we have answer is 2.84. So to evaluate the difference between the means in order to make a decision about our gym programs, we compared the test statistic to a theoretical value from the t distribution. Now this activity involves four steps. First step, that is, we decide on the risk we are willing to take for declaring a significant difference. So for that, the body fat data, we decide that we are willing to take a 5% risk of saying that the unknown population means for men and women are not equal when they are really are. So in statistics, we speak the significance level denoted by alpha is said to be 0.05. It is a good practice to make this decision before collecting the data and before calculating the test statistics. We calculate now the test statistics. Our test statistics, which has come, is 2.80. In the previous slide, if you can see. So now we find the theoretical value from the t distribution based on our null hypothesis, which states that the means for men and women are equal. Now, most statistics books have they will calculate the value based on the tables for the t distribution. So we can also find the tables online. And most likely situation is that if we use the software, we will not be using these printed tables. Now to find this value, we need the significance level, that is alpha is 0.05, and the degrees of the freedom. So the degrees of freedom are the based on the sample sizes of the two groups. Now here we have df is equal to n1 plus n2 minus 2. So that is 10 plus 13 minus 2 is 21. So the t value with alpha 0.05 and degree of freedom 21, the value is 2.08. So we compare this value of our statistic to the t value. Now 2.8 is greater than 2.08. So we reject the null hypothesis. That means the body fat for men and women are, so we will reject this hypothesis and we will conclude that we have evidence that body fat in the population is different between men and women. So what are the statistical details underlying over here? Let's see that whether this two sample t-test has proved accepted our null hypothesis or not. So our null hypothesis is that the underlying population means are the same. That means the null hypothesis H0 is equal to mu1 is equal to mu2. The alternative hypothesis is that the means are not equal. So this can be written as H A is equal to mu1 is not equal to mu2. So we calculate the average for each group and then calculate the difference between the two averages. And this is written as x1 bar minus x2 bar. So we calculate the pooled standard deviation. Now this assumes that the underlying population variances are equal. So the pooled variance formula is written as SP square is equal to N1 minus 1 into S1 ka whole square plus N2 minus 1 into S2 ka whole square, that is standard deviation, upon N1 plus N2 minus 2. This we have already done in the last discussion. Now, as the formula shows that the sample size for the first group, that is N1, and the second group N2. The standard deviations for these two groups are S1 and S2 as already reported to you. So the estimate allows the two groups to have different numbers of observations. Now the pool standard deviation is the square root of the variance and is written as SP. So what if our sample sizes for the two groups are the same? So in this situation, the pooled estimate of the variances is simply the average of the variances of the two groups, as you can see over here, S1 whole square plus S2 whole square upon 2. Okay, so it is the average of it. So here the test statistics, as we have seen, the T is equal to x1 bar minus x2 bar upon SP under root 1 upon n1 plus 1 upon n2. Now the numerator of the test statistic is the difference between the two group averages. So it estimates the difference between the two unknown population means. The denominator is the estimate of the standard error of the difference between the two unknown population means. So when we compare the test statistics to t value with our chosen alpha value and the degrees of our freedom for our data, so what we can say using the body fat data, we can say that at alpha at 0.05, the degree of freedom are based on the group sizes. So which we have calculated to be 21. So we can write that t is equal to 0.05 comma 21. So likewise we can write our t statistics. So t is the value with the alpha where alpha is 0.05 and 21 degree of freedom and the value is 2.080. So there are two possible results from our comparison. The test statistic is lower than the t value, that is the first value. So we fail to reject the null hypothesis of equal means. So we can conclude that the data support the assumption that men and women have the same average body fat. The test statistic, if it is higher than the t value, then we reject the hypothesis of equal means. So we do not conclude that men and women have the same average body fat. Okay. So now, what if the t-test is to be found with unequal variances? So when the variances of the two groups are not equal, we cannot use the pooled estimate of the standard deviation. So instead, we take the standard error for each group separately. So test statistics will become like t is equal to x1 bar minus x2 bar divided by s1 whole square upon n1 plus s2 whole square upon n2. So here the numerator of the test statistic is same, but it is the difference between the averages of the two groups, and the denominator is an estimate of the overall standard error of the difference between the means. Now it is based on the separate standard error for each. So here we can see the degree of freedom is calculated for the t-value is more complex with unequal variances than equal variances and is usually left up to the software packages. So the key point to remember is that if you cannot use the pooled estimate of standard deviation, then you cannot use the simple formula for the degrees of freedom. Testing for normality. Now, the normality assumption, as we have seen, is more important when the two groups have small sample sizes than for larger sample sizes. So, normal distributions are symmetric, which means they are even on both sides of the center. So, normal distributions do not have extreme values or outliers. We can check these two features of a normal distribution with graphs. Now, earlier we have decided that the body fat data was close enough to normal to go ahead with the assumption of normality. So the figure has shown a normal quantile plot for men and women and supported our decision. So we test each group separately. Now, both the test for men and the test for women show that we cannot reject the hypothesis for a normal distribution. We can go ahead with the assumption that the body fat data for men and women are normally distributed. So we can see the normality distribution over here. Okay, the figure here shows the two sample t test Okay, so it is normal, as we can see. Okay, differences, standard error, upper difference, okay, confidence level and everything. So here we can see now it is there's sufficient evidence that the data is normally distributed. So now the results of the true sample t-test that assumes equal variances are the same as our calculations earlier. So the test statistics is 2.79996. Now the software shows results of a two-sided test for one-sided test also and for one-sided test also. So the two-sided test is what we want. That is probability is greater than the absolute value. Our null hypothesis is that the mean body fat for men and women is equal. So our alternative hypothesis is that the mean body fat is not equal. Now, the one-sided tests are for one-sided alternative hypothesis. For example, for a null hypothesis that mean body fat for men is less than that for women. So in that case, we can use one-sided test. Or we can reject the hypothesis of equal mean body fat for the two groups and conclude that we have evidence that body fat differs in the population between men and women. The software shows a p-value of 0.0107, and we decided on a 5% risk of concluding that the mean body fat for men and women are different when they are not. So it is important to make this decision before doing the statistical test. Now, we can also see that the result for the t-test that we do not assume equal variances. So this test does not use the pooled estimate and the standard deviation. As we mentioned above, this test has a complex formula for degrees of freedom. So we can say that the degrees of freedom are 20.98. The software shows a p-value of 0.0086. Now again, with our decision of 5% risk, we can reject the null hypothesis of equal mean body fat for men and what if I have more than two groups? Again, just like the one sample test. So if we have more than two independent groups, you cannot use the two sample t-test. You should use multiple comparison method. ANOVA or analysis of variance is one such method. Other multiple comparison methods include Tukey's grammar test of all pairwise differences, analysis of means, that is ANOM, to compare group means to overall means, or Dennett test to compare each group mean to a control mean. What if the data is not from normal distribution? Obviously, if your sample size is very small, it might be hard to test for normality. So in this situation, you might need to use your understanding of the measurements. For example, the body fat data. The trainer knows that the underlying distribution of the body fat is normally distributed. Even for a very small sample, the trainer would likely to go ahead with the t-test and assume the normality. What if you know that the underlying measurements are not normally distributed? Of course. What if your sample size is large and the test for normality is rejected? In this situation, you can use non-parametric analysis. This type of analysis do not depend on an assumption that the data values are from a specific distribution. So for the two sample test, t-test, the Wilcoxon rank sum test is a non-parametric test that can be used. Now coming to the next topic, that is the paired t-test. What is paired t-test? It is a method used to test whether the mean difference between pairs of measurement is zero or not. When can you use this test? Of course, you can use this test when your data values are paired measurements. Example, you might have before and after measurement for a group of people. Also, the distribution of differences between the paired measurements should be normally distributed. One question arises here. What are some other names for the pair t-test? Is there any other? The pair t-test is also known as the dependent sample t-test. the pair difference t-test, matched pair t-test, and the repeated sample t-test. So it is known by four different names, but the test is the same. What if the data is nearly normally distributed? Isn't nearly normally distributed. So your sample sizes are very small, then you might not be able to test for normality. So you might need to rely on your understanding of the data, as I have been saying again and again. And you can use a non-parametric test that doesn't assume normality. Now, using the pair t-test, what do we need to do the first? For the pair t-test, we need two variables. One variable defines the pair for the observation, and the second variable is the measurement. Sometimes we already have the pair differences for the measurement variable. Other times we have separate variables for before and after measurements for each pair and need to calculate the differences. So now coming to this pair t-test with an example. Suppose an instructor wants to use two exams in her classes next year. Now, this year, she gives both exams to the students. She wants to know if the exams are equally difficult and want to check this by looking at the differences between the scores. If the mean difference between scores for a student is close enough to zero, she will make a practical conclusion that the exams are equally difficult. Now, here is the data on the screen as you can see. We have student's name, exam 1 score, exam 2 score, and the differences. So if we look at the table, we can see that some of the score differences are positive and some are negative. Now here we might think that the two exams are equally difficult. So other people might disagree. The statistical test gives a common way to make the decision so that everyone makes the decision on the same data. So now let's check the data. Let's start by answering, is the pair t-test an appropriate method to evaluate the difference in difficulty between the two exams? Now here, the two subjects are independent. That means each student does their own work on two exams. Each of the paired measurements are obtained from the same subject. So each student takes both the test. The distribution of differences is normally distributed. So we will assume this is true and we will test this later. So we decide here that we have selected a valid analysis method, that is the pair. So this 1.3 is close enough to 0 for the instructor to decide that the two exams are equally difficult or not. Now the question arises, how to perform this t-test? So I'll further explain the principles underlying the pair t-test in the statistical detail section. So here we can see that this beginning from this t-value calculation, we'll start with the test statistics. We will then need the average difference, the standard deviation of the difference, and the sample size. So we now have the pieces of our test statistics, and we calculate our test statistics as you can see over here. T, okay. This is the average difference upon standard error. That is the values of 1.31 and divided by standard error, that is 1.75. That this we can see through this histogram and the summary statistics. Okay. So the T value comes to 0.75. Okay, so average score difference, that is the XD bar is 1.31. That is the mean, as we can see over here, this mean value. So here we calculate the standard error for the score, that is already 1.75, which I have already taken over here. Okay, so now seeing to this statistics, we need to make our decision. We need to compare the test statistic to a value from the t distribution. Now, this activity involves four steps. We need to decide on the risk we are willing to take. That is, we have taken 5% risk. Okay. Now, this 5% risk, let's say that we want to say the mean exam score difference is 0, when in reality it is not. So the statistics speak that we set the significance level denoted by alpha, that is 0.05. It's a good practice to make this decision before collecting the data and before calculating the test statistics. So we calculate the test statistics and our test statistic is 0.75. That is, you can see over here, 0.75. And then we find the value from the t distribution, which we have already seen how to find it out in the previous examples. So if we are doing it with books, obviously we'll be needing the tables for the distribution. Otherwise, we can do it through software. So in most likely situation is that we use the software for the analysis and we do not need any printed tables. So we need to find this value. We need the significance level, that is 0.05, degree of freedom, that is df n minus 1, that is 16 minus 1 is 15, and the t value with alpha at 15 degrees of this thing is 2.131. So we compare the value of our test statistic, that is 0.75, to the value t value. So our 0.750 is less than 2.131. So we cannot reject our idea that the mean score difference is 0. So we make a practical conclusion to consider exams as difficulty. So, seeing to the statistical details, our null hypothesis is that the population mean of the difference is 0. The null hypothesis is written as S0, and where mu d, that means mu is equal to 0. And the alternative hypothesis, that is the mean population is not 0. Okay, so this is written as HA is mu d is not equal to 0. Now we calculate the standard error, that is SD upon under root n, and the formula here we can see T is equal to mu D upon S upon under root n. So we compare the test statistic to T value with our chosen alpha value and degrees of freedom. So in our exam score data example, we have set alpha to be 0.5, 0.05. So and degrees of freedom is n minus 1, that is 16 minus 1, that is 15. So we can write the statistical value t. So we write this at t at 0.05 and degree of freedom 15. The value is equal to how much? So we'll calculate it. So the test statistics is lower than the t-value. So we fail to reject the hypothesis that the mean difference is 0. The practical conclusion made by the instructor is that the two sets are equally difficult. So next year she can use both exams and give half the students one exam and half the other. So the test statistic is higher than the t-value. In that case, you can reject the hypothesis that the mean difference is 0, and the practical conclusion made by the instructor is that the tests are not of equal difficulty. So she must use the same exam for all the students. Okay. Now testing for normality. The normality assumption is more important, as we have seen in the past examples, for small sample sizes than for the larger sample size. So normal distributions are symmetric, which means they are equal on both sides for. Okay, normal distributions do not have extreme values or outliers. We can check these two features of a normal distributions with graphs. And earlier we have decided that the distribution of exam score differences were close enough to normal to go ahead with the assumptions of normality. So here we can see that normal quantile plot for the data and also supports our decision. So we can perform this formal test for normality using software also. Now question arises, what if my data are not from a normal distribution? So if the sample size is very small, it is hard to test for normality. So in this situation, we need to use our understanding of the measurements. For example, for the test scores data, the instructors like they know that the underlying distribution of score differences is normally distributed. So even for a very small sample, the instructor would likely to go ahead with the t-test and assume the normality. Now, if we know the underlying measurements are not normally distributed, then if and our sample size is large and the test for normality is rejected. So in this situation, what will you do? In this situation, we can use a non-parametric analysis. And these type of analysis do not depend on an assumption that the data values are from a specific distribution. So for the pair t-test, a non-parametric test is the Wilcoxon signed rank test. Now here we have some examples. Uh, Data is given. I will now leave to the viewers to solve this. Although the examples are already solved, so you can take this exercise, do it, and try on your own. And I have given two examples, so they both are solved. One is with a pair test, and so wishing you all the best. I hope you were able to understand all the concepts which has been explained in this exercise. If you feel any doubt, if you have any doubt, you can feel free to contact me. uh, very soon I will be displaying my email ID and my contact number and my YouTube channel also in the coming sessions.